that this value has changed. So earlier it ended with B250, now it ends with 7248, which implies that the position where the string got stored has changed. Now, if I compile this program again, exact same program, I again output its value, it would remain same, right? You can try this a couple of more times, and every time you will observe that this value might sometimes remain same and might change. So that tells us another important property of pointers, that the inherent position of pointers are never guaranteed. So if you take this same program, run it on my machine at some other time, you will get some other value. You take the same program, run it on your machine, it would have a different value because the underlying address position has changed. So that's kind of how pointers work. And generally speaking, they are not really the best thing that you should do in a program in production. And there are a couple of reasons too. So for example, I have pointed to the address of alpha in string star address, right? Now imagine I'm doing that in a for loop, right? So I'm allocating a lot of memory and it might be leak. So whenever you use pointer, kind of make sure that when you are allocating some space, either always use it or always deallocate it. Don't just let it be there, right? So that's kind of an important thing. Also, thing that you can probably dwell also is that if you see G++ version, so this is G++13, right? G++13 has support for C++ version 11, and C++ version 11 has included smart pointers into it. So a lot of deallocation happens automatically and no longer needs to be done manually. So I suggest if you are writing a program with pointers, probably use those instead of raw pointers, right? Pointers is a thing that you should ideally address in pointers is something you ideally use to understand the underlying concept of the language and avoid using it in production, right? Any questions so far? Okay, cool. I plan to have this as a collaborative session. So if you guys do have any questions, do share. I'll try to answer all of them. So another way you can think of pointers is this. So for example, you would have read that integers int in C++ takes up say 4 bytes, right? How do I verify that int takes 4 bytes, right? I don't have any way to verifying that. You can verify that with pointers. So here I have allocated a vector of int called as r. I'm pushing back one int into it, and I'll push back another value into it, right? So now array has 1 and 2 inside it. Array 1 should point to value 1. Array 1 should point to value 2, right? Address of array 0 should point to address where 1 is getting stored in this array, and array address of array 1 should point to where value 2 is getting stored inside the array. Now if 1 takes up 4 bytes and 1 is in say 1 byte, right, some x plus 1 byte, right, then this value 2 should always be in x plus 5 byte, right? Because x plus 1 to x plus 4, 1 is getting stored there. From x plus 5 to x plus 9, 2 should be stored there. So essentially both of these values should have a diff of 4 bytes, right? If this points to say 0, something like OX100, then address array 1 should necessarily point to 0x104, right? Because array 0 is a 4 byte long space. And this exact starting value might be different, as I showed here, right? The starting value of a pointer can be different, it is not guaranteed, but the diff should always match, right? So we'll just run this and check this. right? So see, initial value is 0x141605D90, right? It's a random value where the value 1 is getting stored inside the array. But the next value is necessarily a plus 4. It's 94 at the end, right? Because 1 takes 4 bytes. Now let us say I declare this as long, right? I'm still storing 1, but now this 1 would be stored as a long, and long takes twice the memory of int, so it should be 8 bytes long. So if this is x plus 1, this should be x plus 9. If this is 100, then this should be 108. Let's verify that too. Yeah. So we can see that the starting value is 90, but the ending value is 98 because 90 to 97, one long is stored there. So that's generally how you use pointers. There are interesting things that you can do too. So, for example, I can say long star address of 1, and I'll store this here. Long star address of 2, and I'll store it here. Right? I can print these two values and they would be identical because I'm pointing to them. They are not reallocations. Right. So ideally this value and this value should be similar, and this value and this value should be similar. They point to the same address. Yeah. So we can observe this, right? Storing the pointer's address is identical to the pointer location itself. And this is true for both the pointers. So now you can do something like say address of 1, whatever value is stored here, I want to overwrite it as 3, right? So I'll do something like this. Okay, so rather than that, let us say I have address of 1 stored, right? I already know the value, right? Yeah, so address of 1 is same, what we had observed. Now I want to know at this position what value is stored, right? So I can also know this. So this tells me that value stored at address of 1 is 1. Now, how did I access it? I accessed the value at that address from star. And how does GCC knows that this is value 1? Because address of 1 is a location. I have also declared that address of 1 is an address of long. Now G++ knows that address of 1 starts at some position. It is the address of long, and long is 8 byte longs. So the next 8 bytes are this long value, right? It will just calculate what is stored in the next 8 bytes from this address and just prints this when I'm doing star address of 1, right? That is why I can get 1. Now I can change the value inside the original array by just changing what is stored at this address, right? So we can check this, right? Check this out also. So let us say I want to store value at address 1 to be 3, right? Now if I just print this same line after this, right? This is say before, and this is say after. Right, and I'll just print a line. So we know what we are printing. Yeah, we need a semicolon here. Yeah, so this is once again an interesting part. I forgot in line 13 and 16, 19, 13 and 19 to add a semicolon, right? So now my code is not a valid C++ code. So G++ will tell me whenever I compile G++, it will tell me that, okay, you have a function that is called as int main. And in line 13, I expected a semicolon. You have not added this. So it tells me an error here and here. So I can just go back and add this. So a compiler is also a really good friend of you when you are coding, because you know your errors before running them, right? These kinds of errors are called as syntactical errors, an error in the syntax of your code, and you can catch them at compile time, right? This G++ thing. Now when I'm running a dash a slash a dot slash a dot out, I'm running my program. If I find a bug here, then that would be called as a runtime bug, right? So yeah, we can see value stored at address of 1 is 1 here, but after I have done value allocation, I'm printing it is value 3, right? So this is interesting because I have some address. I know that that address is of a long. I can change that value. But even more interesting thing is, if I printed array 0 earlier, later, and I'll print this value before allocation also, right? And I'll print array 2 too. Right. So you see, array 0 is 1, array of 1 is 2. What we had allocated here, right? Push back 1, push back 2. This is expected. But when I changed address value at 3, an address of 1 pointed to whatever was stored in 0, and I changed it to 3. This value came as 3, right? You can see here. This is fine, but the underlying value at this address had also changed, right? Because see, array 0 is now 3, array 1 remains to be 2. So this is an interesting thing that you can do with pointers. Rather than passing the variable itself, you can just pass a reference of the address and change that value. So I just used address position and changed the values rather than overwriting on array 0. I overwrote on the address itself. Once again, there is literally nothing that you cannot do with pointers and can do with pointers. So it's not like that this is something X that you cannot do with pointers and now you know pointers so you can do this, right? There's nothing like that. In general, adding pointers in production code is a bad idea, but when you are trying to debug things, when you are trying to write a proficient solution, sometimes pointers makes more sense. So that is why you should know what a pointer is. I suggest avoiding its use in general, right? Whatever is in this file is mostly how you want to use a pointer, right? So when you want to know the address, add an ampersand before the variable so you can know that address. Now you want to store that value, just define what data type is getting stored at that address. In this case, it's a long, so it's long star now. If it was int, it would have been an int star. And then you can do whatever you do with the standard variable. And you can play around with it. There's also an interesting thing called as reference. I suggest you check that out after this lecture. So check two things: smart pointers and references. So we'll know a little bit more about how you can use pointers in production systems, right? Now one more thing you might have observed, right? Every time I compiled a file, it got overwritten to a dot out, right? This is this a dot out file. You can open it also, right? It's a binary file. You cannot read it. It's a file your computer knows to execute, right? Now let us say I want to have a dot file, but I want its name to be something specific, right? So for example, whenever I compile pointer1 CPP, it gets written to a dot out. When I compile pointer2, it also gets written to a dot out. I cannot have separate binaries. So you can actually do that. Just do g++ dash o pointer1 dot out and then pointer1 dot cpp. So g++ will think that it has to compile pointer1 cpp and the output needs to be written in the file after dash o. So that file is pointer1 dot out. So if I run this, I'll get a pointer1 dot out file. This tells me that a binary has been created in dot out file. I can do the same thing for say 1 dot out 1 dot cpp and pointer2 dot out should be written for pointer2 dot cpp. Once again, it tells me there is some error in pointer2. So it tells me that it's at line 24. So you can see at 24 there is this error. So I'll just remove it, compile it again, and yeah, it gets compiled. And you'll see that I have different binaries now: 1 dot out, pointer1 out, and so on. Right. So you can use flags in G++ to compile your program faster. Right. So you can use flags with G++ to do a lot of cool things. Right. One thing, when flag is dash o, it defines the output file. Another interesting thing that you can do is use dash o capital O1 and define one CPP. So it compiles a program for a certain infrastructure. So sometimes you might want to write a same program but compile it differently for different targets, right? Your code should probably run on a system that has a memory constraint, i.e. low RAM, but a very fast CPU, right? So you should use dash o3. If say you have a system which has a lot which does not have a constraint on RAM, your memory, but has a constraint on your CPU power, then you want it to run fast, right? So you want to use dash O2, right? So you can define different flags itself here, O1, O2, O3, to kind of define what do you want to optimize over RAM, over memory. You want to optimize both, right? So you can use dash O to do that. You can use a lot of other things also. So say I'll use WALL wall, right? So it will give me warnings for all of the things that would compile correctly, but might be a problem at runtime, right? So remember I told earlier that there are two kinds of things: a compile time bug and a runtime bug, right? This is an example of a compile time bug. A compiler told me this. It could be possible that there is something that gets compiled correctly at compile time but might be a problem at runtime, right? So the compiler can also tell me that, okay, I'm compiling this file, but this file might be a problem for you at runtime. How do I make the compiler tell that, okay, tell me that if there are some of these issues in the file, I'll use WAL. So it will give me warning for all the issues in the file. So you can use a different kind of flags for your G++ to compile things correctly, right? Another thing is GCC is also a compiler. GCC is used to compile typically C files. G++ is used to compile C++ files. You don't need both. Just to install G++, it will compile both files, C and C++, right? And another thing I wanted to touch upon in your build system itself is a make file, right? So as you have observed, there are a lot of flags, and you don't want to remember everything, right? Who really remembers all the flags? So you can just write a make file that will compile things for you. So I can say something like compile G++ dash w all dash o2 optimize for time over memory dash o 1 dot out 1 dot cpp. This will compile first file, right? And I'll just write this, and then I can just do make compile, and it will compile things for me. In this case, it tells me that this is a fatal error. Bit C std c++ is not in the is not found. So because g++ points to clang in my system, right? So I can just point it as g++ 13 and it would run properly. Yeah, so it runs properly now, right? Similarly, I can define same things for pointer 1 and pointer 2. And everything will compile now, right? So now I don't have to write all these everything every time to compile things. A simple make compile will compile everything, right? So that's an interesting thing you can use to compile your code. Now you would have observed that we do have a warning here. So see, this is a difference between an error and a warning. Earlier we had a error, so it was fatal error printed in red. Now I am getting a warning. It's not a fatal warning, so it's printed in pink. It says warning unused variable address of 2. This happens because of w unused variable long address of 2. So if you see, I have defined a variable here, right? Long star address of 2, and I'm no longer using it, right? Address of 2 is not used anywhere else in the program. So it says that you have defined a variable but you are not using it, right? So this is something called as a, as what I explained, a memory leak. I defined a variable I never used in the program. Now imagine I was doing this inside a for loop. I would have allocated a lot of memory but would have never used it. So it tells me at compile time that this program is syntactically correct and will compile properly, right? If I run pointer 2, it would run. This runs because there is no compile time error. But it gives me a warning that you have an unused variable that is address of 2 on line number 11. You are not using it, so why are you allocating it? So if I just print this off, I just comment this out and do make compile, I will not get the warning because now I'm not using that variable, right? Or I cannot comment it and just print this. I'll still not get the warning, right? So let me print it here after, say, a line. So yeah, now I did not got that warning, but I get a new warning which says that this is a error. This is a compile time error, right? See, it's an error, not a warning. It says invalid operand of type itna and itna to binary operator plus. So it essentially says that this is a string. This is a value of a address. Why are you adding them, right? So if I do this, it would compile again, right? It compiles again, and I can print pointer 2, and it prints. There is now no warning. So either don't use a variable, or don't declare a variable, or declare a variable and use it. You won't get a warning then, right? So that's something interesting. Now if I just comment this out, I'll still get this warning because I'm not using the variable. Yeah, see, I get the warning. And notice one another thing about the warning. It says that this warning is because of the flag dash w unused variable, right? But in my make file, I have never defined dash w unused variable, right? That is because I have defined dash w all, right? W wall is basically dash warning all. So it makes G++ give warning for all types of warning that it can give. One of those warnings is W unused variable. So essentially, you don't need to define all explicit variables. You can just do W all and it will give you all the warnings, right? So you have address of 2, and if you don't want that warning, you can just print that value. You won't have that issue. See, it compiles fine without complaining. So that's the general idea around things. Um, is there any doubts till now? Yeah, what's the use of pushback keyword? Yeah, so that's a great question. Basically, um, inside of bits stdc++.h, there is a definition for what is a vector, right? This value. And a vector has a function called as pushback. So basically, a vector is like a space. It's like an empty space at this point. When I'm defining, it's a long vector long array. It's basically this. Now, when I say I'm pushing back 1, I'm basically adding 1 to this array. Now, when I'm saying push back 2, I'm doing 1. 1 was already there. Now I'm just pushing 2 inside it too. So a vector becomes like this. So how do you verify this? There is a simple way. Just have a new file. Right? I'll push 2 values as I was doing earlier. But now I'll also write a simple function that displays what's stored in a vector, right? So print add, right? That's a simple value. It takes up the value, it takes up the vector and just prints. Or okay, let's not use this syntax. Right? So this will print whatever is stored in the array. So I'll print the array after every line. So we know what's happening. And just add a line here. So we can visually see the change. Yeah. So initially when I called print array, it just happened after I declared array. So array is empty, nothing gets printed here. Then I pushed back 1. So now array has 1 value stored inside it. When I'm printing it, it's getting printed as 1. Then I have pushed 2, so it gets printed as 2. You can pop values also. So say I do array.pop and then I print the array again. 2 would have now popped out of the array and only 1 should be present now. So you can do something like pop back. Yeah. Yeah. So now I popped the last value in the array. So 2 got removed and now only 1 was here. So that's how you use pushback and pop. Yeah, C++ is used extremely in industries. So almost all of the programs you write are written in Unity or different game engines. All of those game engines are written in C or C++, and your debuggers are written in C++. Compilers are written in C++. If you use Ubuntu, you use Linux kernel. Linux kernel is written in C. So almost all of the infrastructure you use is written in C++, and anything you do outside of building simple RESTful APIs or CRUD APIs is essentially C++. It's like a extremely important language both in the industry and in understanding how programming really happens, right? So even if you don't plan to use it in industry, I suggest learning it thoroughly. It will help you understanding the underlying concepts of how trace works, what is a stack, what is a heap, how does compilation happens, and all those things. Any other questions? Okay, cool. So we can probably end this session then.
No.
Okay. Okay, thanks for inviting me, Code Campers, and all the folks attending the talk. If you have any doubt, feel free to reach out to me through LinkedIn. I'll be happy to explain things.
So, I would like to take a moment to express our heartfelt gratitude. Firstly, a big thank you to each and every one of you being here today. Your enthusiasm and dedication to mastering DSA and algorithm truly inspires us. A special thanks to our fantastic guest, Mr. Karthike Tiwari, for sharing their invaluable expertise in C++ basics and pointers. Thank you.
Thank you. Thank you, Via.
Thanks.
Thank you, Bhaiya.
Thank you.